Okay, we're going to go ahead and get started. Hello and welcome to NOAA's National Ocean Service Science Seminar Series. My name is Tracy Gill and I'm the coordinator for this seminar. Today is the third of a 4-seminar series and you'll hear more about it after a few seminar logistics. Since we have 5 speakers today, people in the room, please hold your questions until after the speakers have finished. And folks online, you can type your questions into the chat box at any time, but we'll not get to them until all speakers have presented. If you are interested in getting a PDF copy or MP4 recording of today's presentation, please contact Laura Newcomb, Gina DiGiantonio, Emma Kelly, or myself, Tracy Gill, at NOAA.gov, and we will be happy to send you a copy. If you are not on NOAA's weekly science seminar list but you'd like to be, please contact me and I will add you to the list. Folks in the room, silence your phones and sign in. And now I will turn the floor over to Laura Newcomb, Program Analyst at NOAA's Office of Atmospheric Research, working with laboratories and cooperative institutes. Laura?
Welcome to this webinar on a robust and effective research and development enterprise, the third of 4 seminars in the inaugural NOAA Science Report Seminar Series. The sponsors for the NOAA Science Report Seminar Series include the NOAA Research and Development Enterprise Committee, Emma Kelly, Gina DiGiantonio, myself, and the NOAA NOS One Science Seminar Coordinator, Tracy Gill. The NOAA Science Report is an annual report that highlights NOAA's scientific accomplishments for the year. The NOAA Science Report celebrates NOAA's research and development in 4 sections. 1, the introduction, science highlights, bibliometrics, and NOAA's scientific workforce. Together, these sections highlight how NOAA's research products impact the lives of all Americans. The 2019 NOAA Science Report has been released on the NOAA Research Council website. Please access the full report via the website to read further about NOAA's scientific accomplishments in 2019. The link is up on your screen, and we will also put one in the chat box to take you directly to the report. The report spans the entire range of NOAA's mission, and there are 64 stories featured in the 2019 NOAA Science Report. Today, we welcome 5 speakers whose work is featured in the Science Highlights section on a robust and effective research and development enterprise. Our speakers today include John Forsyth, who received his bachelor's from the University of Maryland and his master's from Colorado State University. He is an expert in satellite remote sensing with a specialty in microwave remote sensing and serves as a PI on several NOAA JPSS, GOES-R, and hydrometeorology testbed projects to improve and deliver new blended products to forecasters. Brian Costa graduated from Middlebury College with a joint degree in biology and environmental studies and from the University of Maryland College Park with an MPS in geospatial sciences. His research interests include novel applications of state-of-the-art remote sensing and commercially available geospatial technologies. He is currently co-located with the Channel Islands National Marine Sanctuary in Santa Barbara, California. Josh London received his bachelor's in wildlife sciences from the University of Washington College of Forest Resources and a PhD from the University of Washington School of Aquatic and Fisheries Sciences. Josh is currently a wildlife biologist with the Polar Ecosystems Program, and his research focus is population assessment and ecology of harbor seals. Maria Kavanaugh received her bachelor's in zoology, master's in marine ecology with statistics and oceanography minors, and PhD in biological oceanography with a statistics minor from Oregon State University. She is an assistant professor at Oregon State University, and her research specialties are seascape ecology, remote sensing, and global change. Joaquin Trenanes received master's and PhD degrees in physics from the University of Santiago de Compostela in 1993 and 1998, respectively. He is an associate professor at the University of Santiago de Compostela and works as an operations manager of the Coast Watch Caribbean and Gulf of Mexico node at NOAA AOML in Miami. His research interests are focused on remote sensing, oceanography, and scalable data management and analysis. Each of the speakers will give a 10-minute presentation, and then we will have a question and answer session at the end. Take it away, John.
Okay, well, thank you very much. My talk is about a new water vapor product that forecasters for the Weather Service are using, and something we developed here at CIRA, which is a cooperative institute, a NESDIS cooperative institute in Colorado State University in Fort Collins. And just quickly wanted to acknowledge, I can't list all my colleagues. There's many of them there, including quite a few operational forecasters in the Weather Service. And the start of this work was actually with NASA in around 2012. So we've evolved it some from there, and we have a product that's just about ready to get into operations. So I'll describe this product for water vapor, why it's important, and how forecasters are using it, and what the future is. So just a brief background. I always think of water vapor as fuel. It's what drives flooding rain events, and with the changing climate, the water vapor in the atmosphere has been increasing as it warms. Over the Gulf of Mexico in the summertime, about 6% since per decade, or 6% total since the late 1980s. So forecasters need to see how this water vapor is flowing in the atmosphere at different layers. I would sort of term this the plumbing of these heavy rain events. Where is the water vapor coming from? How much is there? How much will it last? And these source regions for heavy rainfall are typically over the ocean, maybe thousands of miles away from where the flooding events are occurring. So that clearly points to the need to have satellites to track these. That's really the only tool that we can really get the whole picture with. Floods are having an increasing impact in the United States just in terms of damage and loss of life. I have a few examples from the past few years there. So I would say that this problem is getting worse, not just due to more water vapor, but also due to more urbanization, people living in more flood-prone areas, and so forth. So just a little bit of the overview of the statement of the problem, and the theme of this series today is about the effective research and development enterprise. So I'll come back to that, some ways that being at a cooperative institute, NOAA Cooperative Institute, has really helped us here at CIRA to do that. So traditionally, NOAA operates geostationary and polar orbiting satellites, and they have different capabilities. The sensors that create the products that I'm going to talk today use passive microwave information, which is radiated from the Earth, that tells us a lot about the atmosphere, the temperature, how much water vapor. I think of these sort of like when you go to the doctor and get an X-ray. You can see through into your body what's in there, and that's very much what microwave data is like. Although it's a passive technique, we're not actually sending microwave data at the Earth with these satellites. It's measuring what's naturally there. Microwave data are hugely important to inform weather forecast models. In fact, most studies indicate they are the #1 impact on the data source impact on weather forecast models globally. And a lot of that reason is, the reason for that is because the global coverage and that data over the oceans, the weather that's going to affect the eastern U.S. in, say, 5 days is out over the Pacific Ocean right now. So in order to get that right, you need to know what's going on out there. But historically, they've only been on the polar orbiting low altitude satellites, which has been difficult to use. They're not something forecasters have traditionally used. So in order to get this data to forecasters, we've created something we call blended multi-sensor satellite products with advection. This chart here is sort of, you can think of it as a clock, and we have these satellites coming over at different times. And the key takeaway from this is that these orbital planes you see of the satellites that come over twice a day, they're not evenly spaced. They tend to cluster at certain times for a variety of reasons. These are 3 different sets of satellites from NOAA, from the METOP satellites from Europe, and a couple of military satellites on there. So what we do is we take water vapor retrievals from those with the microwave information through something that's called MIRS, which was a system developed by NOAA, and we take those and map those into a product, and then we use winds to basically make it appear as if these satellites are coming over every hour, even though they're not. So what that has given us is an example of this new product we call advected layer precipitable water, or ALPW, and this is 4 layers in the atmosphere. You can think of it as near surface, a couple in the middle atmosphere, and then higher up around the top of the troposphere, where jet aircraft fly. And I do have the link down there. We do have this operating in real time, so you can look at this every hour to see how water vapor is flowing. But just even in this example, you see off of the United States some plume of moisture coming out of the tropical East Pacific that's going to go up into the southeast U.S. and add some of that fuel for heavy precipitation. So how is this used? I have a what's called a mesoscale precipitation discussion here from the NOAA's Weather Prediction Center in College Park, which sort of stands watch over the United States, looking for conditions that are favorable for flooding on different time scales, from hours to days out. But we have our data flowing into that facility that we produce here in Colorado and send into the Weather Prediction Center. And this is a very typical use. You see that they say that the Sierra layered precipitable water reveals a plume of moisture that extends through a great depth of the atmosphere and originated about 10 degrees north down in the tropical East Pacific. So we track these rivers or pipelines of water vapor with these products. Also, the National Hurricane Center has found a lot of uses for this data. When a cluster of thunderstorms comes out off of Africa, they can look at the environment and sort of tell whether it's favorable for development or not, whether there's dry air in the vicinity, which is very unfavorable, or if this layer precipitable water product shows that there's a chance for growth and for a tropical cyclone to form. So getting the data to forecasters is sort of an important part of what we do here and the theme here. So being at a NOAA Cooperative Institute at a university, we do have 5 federal employees that work here, and they're able to send the data into National Weather Service offices and national centers like the National Hurricane Center and Weather Prediction Center. And I think a real important part of why we're successful doing this is we provide the data to forecasters on their display system, something you'd see in every weather service office called AWIPS-2. And we develop training here, so we're certainly not just referring them to a website. If you've ever watched a professional forecaster go through data, they go very fast. Sometimes they have 6 or 8 screens on their desk. So getting it in their system is important because they're on a schedule. They have to get products out. There could be warnings and other severe weather that's taking their time. So they don't have time to adjust to our system. We have to get it to them the way they like it. And currently, Sierra is sending the data to the 2 national centers listed and 23 weather forecast offices right now. And I have a link. We have a YouTube video there with the training product that forecasters have seen. So a forecaster in Tucson, for instance, just to show the use of this product, said that they look at this religiously especially during the monsoon season. So wrapping up here, the conclusions is this advected layer precipitable water combines 7 polar orbiting spacecraft and provides a new vertically resolved view of water vapor, and it is being used routinely by the National Weather Service forecasters. And so we're producing it here at a cooperative institute, but it's in the process of going into operations, which means it runs 24/7 on NOAA's computers in College Park, and the Weather Prediction Center is the lead on that. And it runs in a division of NESDIS called OSPO, which is the Office of Satellite Products operations, I think, that runs all this and produces it and distributes it throughout NOAA. And with that, I'll stop. Thank you.
Thanks, John. Brian?
Great. Thanks, Tracy.
We can't hear you. Oh, there you go.
Well, good morning, good afternoon, everyone. Again, my name is Brian Costa. I'm a marine ecologist at NCOS. So the title of my presentation today is Leveraging Partnerships and Unmanned Systems to Map Coastal Elevations and Depths. And before I get going, I want to acknowledge the core members of the project team, the folks that did the work. They're listed below, including Tim Batista and Jennifer Kraus from NOAA NCOS, Chris Parrish, Richie Slocum from Oregon State University, Wayne Wright from Wainwright Consulting, and Matthew Shar from NOAA's Office of the Coast Survey. So what's the purpose of this project? What was the need, and what was it designed to meet? Well, many coastal organizations need timely imagery, elevation, and depth data along the shoreline. This information is needed for a variety of applications, from ensuring safe navigation to effectively managing coastal resources. However, coastal areas, particularly the 0 to 5 meter depth range, it's expensive and challenging to map, particularly using conventional technologies like LiDAR and sonar. To address this gap, we tested the ability of unmanned systems and out-of-the-box cameras, as well as photogrammetric software called SFM, or Structure from Motion, to map nearshore elevations and depths. And we tested this approach in 2 marine managed areas, which you see on the left, including Buck Island Reef National Monument on the top in the beautiful warm tropical area of St. Croix, U.S. Virgin Islands, and then also offshore of the Channel Islands National Marine Sanctuary in a very beautiful place offshore of Santa Barbara, California. So who participated? Well, this slide shows a map of the 11 partners denoted by the stars who were involved in this effort. In particular, the partners included academic, federal, NGO, and private organizations. Their geographic locations ranged from the U.S. Virgin Islands to California and Oregon. It's also important to note here that this project is just a successful example of the C-Note Act of 2018, or the Commercial Engagement Through Technology Act. And this act, in a nutshell, directed NOAA to better coordinate across sectors on unmanned systems research. So what did we do in the field? Well, we acquired aerial photographs or imagery at the 2 sites I mentioned earlier using 4 different UAS or unmanned aerial systems, which are pictured in the top left. In total, we spent about 25 days at 11 sites, conducted over 125 flights, and collected over 30,000 images. On each flight, the acquisition parameters, so things like altitude, flight direction, time of day, water conditions, they varied so that we could better understand their impact on image quality and product quality. Depth data were also collected using a sonar mounted on a kayak in Buck Island Reef National Monument and on an autonomous service vessel, or ASV, in Channel Islands National Marine Sanctuary. And the ASV and the data that is collected are pictured in the bottom left. Bathymetric LiDAR was also available in Buck Island Reef National Monument as an independent data set, and you see a graphic of that in the bottom right. So what did we do in the office? Well, after we acquired the imagery, we processed it in SFM, so Structure from Motion software, to develop 2 products, photomosaics and DEMs, or digital elevation models. A photomosaic is a single photograph that's created by combining lots of smaller photographs, and a DEM is a 3D model depicting the topography, the elevations, and the depths for the project area. And the figure that you see in this slide shows conceptually this process of stitching the imagery together to create these 2 products, which you see below. The quality of these products were then evaluated visually and using the depth data sets that I mentioned earlier, including from the ASV, which you see pictured in the bottom right-hand corner. These results were then used empirically to do 2 things: to identify acquisition guidelines and processing workflows that worked well, and then those that didn't, and also to define environmental and operational limitations for this approach. It wasn't going to be successful everywhere all the time, and we knew that going in. So what did we find? Well, at a high level, this approach did successfully create high-quality photomosaics and DEMs. You see an example on the top left from Buck Island Reef National Monument, and then the associated DEM for that location as well. The depths are seen in the blue color ramp, and the elevations are depicted in the green to brown color ramp. So we found that a few things helped improve product quality, and that included flying when the water was clear and calm, using a UAS with RTK or PPK capabilities. So that just means the ability to post-process the location of the drone so you can get a more precise position. The product's improved when you flew at a higher altitude, greater than about 100 meters. It also improved when you collected imagery with more than 75% overlap and side lap, so a whole lot of overlap. We also found that the DEM improved when you corrected the depths for refraction at the air-water interface. So what you're seeing here is just a 2D slice of that pink transect in the DEM above. So looking at it from the side, you have depth in meters on the Y, and then the distance along the transect on the X from start to the left to the end of the transect on the right. The red line shows the raw SFM depth, so not corrected for refraction. The blue line shows the SFM depths corrected for refraction. And then the kind of tan area shows LiDAR depths for that area. And you can see that the blue line closely tracks the LiDAR compared to the red line. The last thing we found was that the products improved when distinct features were on the seafloor. So the black circles that you see there show places where this approach failed to track the bottom, and that was because there weren't any features that it could use to align photographs. So these were flat, sandy areas that were pretty boring. Overall, though, we found that SFM depths correlated well with independent depth data sets, including the bathymetric LiDAR. So what next? So while this effort was an important first step, future research is needed, though, to continue to advance it. We did publish the guidelines developed here as a report in December of 2019. You see a picture of it on the left there. And if you scan the QC code on the top, it'll take you right to the report. Our hope is that other folks will take these guidelines and build and improve on them. In addition to the report, the partnerships that we developed here help catalyze additional 4 new unmanned research projects at NOAA, and those are listed on the right-hand side. Those include working with NOAA's Office of Coast Survey to operationalize this approach on hydrographic vessels, so the vessels, the ships that go map the seafloor. Second, to test the ability of UAS swarms, so flying multiple drones at the same time to calculate depth in the featureless seafloor areas. So those black circles that I showed you before, trying to find a fix for those locations. Third, we're evaluating UAS and hyperspectral sensors to detect harmful algal blooms or HABs in the near shore, particularly from 0 to 300 meters offshore, which is a blind spot for a lot of satellites. And then fourth and finally, we're testing the ability of miniature low-cost AUVs, or autonomous underwater vehicles. So these are vehicles that go deep under the water, for conducting visual surveys in the deep sea. So the objective there is to collect underwater photomosaics and DEMs in places that are really difficult or expensive to access, and to hopefully do more cost effectively. So I'd like to just thank and acknowledge our funding agencies, particularly NOAA's UAS program and my division, NOAA NCOS. Also like to thank all of our partners who provided logistical support to make this work a success, and those include NOAA's Channel Islands National Marine Sanctuary, the National Park Service, including Channel Islands National Park and Buck Island Reef National Monument, the Nature Conservancy, Santa Cruz Island, and University of California, Santa Barbara. I know we're holding questions to the end, but my email address is listed there, and the QC code, if you scan it, it'll take you right to the project page for more information. Thank you so much.
Thanks, Brian. Josh, you're up.
Thanks, everyone, for coming to this webinar. I really appreciate the opportunity to talk to you about harbor seals in the Pribilof Islands of Alaska. I want to start by first acknowledging 2 key co-authors with this project, Aaron Richmond, who's here with me at the Alaska Fisheries Science Center Marine Mammal Laboratory in Seattle, and Lauren Devine, who's a member of the Ecosystem Conservation Office with the Aleut community of St. Paul Island in Alaska. Many of you probably know about harbor seals. Harbor seals are one of the more prominent marine mammals in the United States. They're found up and down the west coast and into Alaska, but also on the east coast. They're very coastal in their nature, and you can see here in this map the range of harbor seals extends throughout much of Alaska, from southeast Alaska through the Gulf of Alaska, out the Aleutians, and up into Bristol Bay. As far as just a general sense of harbor seals in Alaska, we think our current estimate is there's about 200,000 throughout Alaska, but there are actually 12 different stocks that we recognize in Alaska, and trends within those stocks differ. Most of the stocks are increasing or relatively stable. There have, however, been a few stocks, such as the Aleutian Islands, that have experienced significant declines in the past and still haven't fully recovered. That said, none of the stocks in Alaska are currently listed as depleted under the Marine Mammal Protection Act or listed under the Endangered Species Act. I guess we'll first start just how do we count harbor seals in Alaska. One of the things we want to do is figure out how many there are. And this photo here on the top should give you a clue in how we count them, in the sense that we take photos of them while they're hauled out and then go through and count each of the seals in those photos. We typically do this with small aircraft flying at low altitudes of, say, 700 to 1,000 feet, and capture those photos. If you actually I can move the cursor here. Oh. Well, if you look just below the plane, there's actually small dots there that you can see are actually harbor seals in this survey. Thank you. And while we're flying around, we have observers in the plane who take photos out the window, and like we said, bring those photos back, count the seals, and then all that information goes into some fairly complicated and sophisticated statistical modeling that allows us to come up with abundance and trend estimates for each of the stocks in Alaska. You'll notice I mentioned there are 12 stocks in Alaska, but if you've done a quick math, you realize there's actually missing a stock here in this graph, and that missing stock is the Pribilof Islands. So the Pribilof Islands are located in the middle of the Bering Sea. They're very isolated from the rest of harbor seals in Alaska, and in fact probably one of the more isolated stocks of harbor seals in the U.S., if not the world. And very challenging for us to get surveys out there. To get a plane out there to survey is very costly. The weather's notoriously poor, and difficult for us to accomplish what we need to. One thing I'll point out is that the Pribilof Islands are made up of a few different islands: St. Paul Island, Otter Island, and St. George Island. We'll be focusing a lot of the talk today on Otter Island, which is an area just off of St. Paul Island that has a large number of seals. The Pribilof Islands have a unique history in the sense that they're really known for actual commercial harvest of northern fur seals, which are different from harbor seals. They are otariids, similar to sea lions. The Pribilof Islands were part of Russia, a Russian settlement in the 1700s. Indigenous people were actually forcibly moved from the Aleutian Islands to the Pribilofs by the Russians, specifically to work on the northern fur seal harvest. The Russian harvest continued until the mid-1800s, when the U.S. purchased Alaska from the Russians. That included the Pribilof Islands, and there was actually a northern fur seal commercial harvest up until the mid-1980s. But the Pribilofs, because of their location in the Bering Sea, are actually really important for a wide range of species of wildlife, and have been an important component for things such as seabirds, who rely on the cliffs there for breeding and rearing their chicks. And because the Bering Sea and the Arctic in general have seen huge changes in recent years, the Pribilof Islands have also seen dramatic changes in recent years. And if you look at what we know generally about harbor seals in the Pribilof Islands, the counts over the years seem to indicate that there was maybe around 1,000 or more seals present across the Pribilofs in the 70s and 80s, but then there was some sort of decline, and the population has been at some sort of low, fairly stable amount since then. But as I mentioned, we've had a really difficult time getting out there to get comprehensive surveys. So we entered into a collaboration with both the local Aleut community of St. Paul and the Duke University to try to get an idea of the harbor seal stock and attain a comprehensive survey and also compare drone technologies. So we used two different surveys, the EV Plus SenseFly and the DJI Phantom Pro. The SenseFly produced similar images to what Brian talked about, provided some orthomosaics, large-scale mapping, and also allowed us to carry on board. We actually flew two at the same time, allowed us to carry thermal imagery to also look at seals' thermal signatures. The Phantom Pro provided more focal collection of imagery of harbor seals that we could count in a more traditional way, similar to what we've done. The big advantage of the Phantom Pro is that we could launch and retrieve it from a boat, whereas the EV SenseFly, we had to launch and retrieve from land, and getting people ashore in the Pribilofs can be difficult. So the EV was particularly good for mapping applications over large areas. We created this really nice orthomosaic of Otter Island, but there was logistical constraints and weather constraints, especially to launching from land. So the Phantom provided a much better platform. And the great thing here is that the Phantom was piloted by and licensed pilots with the local community of St. Paul. So that gives us an option to really take advantage of their presence in the Pribilofs year-round and to really get a better understanding of how harbor seals use the Pribilofs and throughout the year, which is something that's really unique for us working in such a remote location. And then the price platform, clearly the Phantom is much cheaper, which makes it much more accessible. So with all this effort, we have this comprehensive estimate. Our counts for 2018 and 2019 had an average of about 240 seals. There obviously, though, if you think about it, there are some seals that are going to be in the water at the time of our survey. So we use a correction factor based on telemetry work in other parts of Alaska to get this to an estimate of approximately 540 seals in the Pribilof Island stock. And this represents our first comprehensive estimate of seals in the Pribilofs. And just to kind of look more at that trend, if we just focus on Otter Island, where we have some additional surveys over the years that have been a little bit more consistent, we can see that there is still a sense of a declining trend. And so given that there's a small number of seals, any trend declining like this is something that we really want to pay attention to. You throw on top of that all the large changes that have happened in the Bering Sea over the last few years, and it's really something that we want to keep our eye on, and we're grateful that we now have this collaboration in place to help us monitor these seals in a much better way. One of those things that we also can do is start to look at things like the timing of pupping. So this shows you an example of mother seals with their pups right next to them, highlighted in the green circles, and you can see with the counts, we're able to actually track when the majority of pups are born, and to over time also see if the number of pups born in a given year changes over time. Again, this is stuff that we can't really get access to in remote locations like this with traditional occupied aircraft like we do in other parts of Alaska. So having a local community-led project that allows them to go out and collect data on a regular basis repeatedly over the summer is a real benefit to us. So in summary, I really want to just highlight the importance of the collaboration and the leadership that the Aleut community of St. Paul has provided. It's a real improvement to our understanding of harbor seals in Pribilof Islands. It's a remote and challenging place, and that we can rely on people who actually live there to collect some of this data is great. The Pribilof Islands are likely the smallest stock of harbor seals in U.S. water. Our current estimate is 540 seals, and you know, the estimate and having that is really great for us. Being able to track these numbers over time is great, but really establishing the collaboration and encouraging community leadership has really been just as important. So lastly, a special thank you to the Aleut community of St. Paul and to Duke University, who really helped us evaluate all this technology and get a lot of these key protocols in place. So thank you very much.
Thanks, Josh. Maria?
Yep, I'm on the line. Okay, I'll go ahead and take control. Thank you, everyone, and thank you for everyone who's online and in person. I just want to quickly thank my collaborators, including Joaquin, who will be presenting this effort with us. This effort was born out of the Marine Biodiversity Observing Network, which was formed as a part of a multi-agency effort to observe biodiversity in U.S. coastal waters. It has now grown to a global effort through the work of GeoBond. All right, so our MBON, or Marine Biodiversity Observing Network motivation, stems from two kind of interrelated forces. And that is that the ocean is facing multiple stressors on multiple timescales, including things like changing climate, changing upstream land use, and fishing. These stressors are patchy and they can overlap, and these interactions can create some surprising effects on ecosystems. And the second factor that creates our motivation is that when we actually go to look at these ecosystems and we look at the where we have information on species abundances, their ranges, and their connectivity, we see that we have a growing record of in situ data. But the record is fairly sparse, and there is inconsistent covering globally. So as part of this effort to create some context for our observational measurements, we, as part of the MBON, are drawing from landscape ecology. And before I go into what seascapes are, I want to just point out a few very simple but important differences between seascapes and landscapes. First of all, in the ocean, the primary producers are microscopic and they're neutrally buoyant. So that means that they're quite difficult to see and that they tend to float out from underneath our observations at any given time. If we were looking at this center image here of time, we would see that there's a, I'm going to grab the cursor here. Let's see if I can do that. We can see, we would be able to see if the animations were working. We would see a bloom forming that appears and then disappears in a matter of weeks. So seascapes tend to be ephemeral. They tend to change very rapidly in time. And then if we look at the boundaries of seascapes also, they tend to be diffuse and they tend to also be dynamic. They will expand and contract and move north and south and east and west as the water moves. Again, I apologize, we had some problems with our animations, so I'll be talking you through those as we go through. So we, as part of the MBON and as part of GeoBond and as part of this new partnership with NOAA Coast Watch, we're using seascapes as a framework to relate the organisms, the in situ measurements, to their dynamic habitat. And on the left here, you would be seeing some of the NASA and NOAA polar orbiting satellites that provide information on ocean physics and ocean biology. We are able to classify this imagery in space and time to come up with this dynamic seascape classification. And again, if the animations were working, you would see that the seascapes are expanding and contracting in time. We do this classification on multiple scales at the global as well as a regional scale, and I'll have a picture that shows this regional scale coming up in just a little bit. And then we validate these seascapes using in situ data and partnerships with people on and in the water who are taking measurements on ocean biogeochemistry, biodiversity at multiple trophic levels, and also getting measurements about fisheries in order to better understand fisheries habitat. So as part of the MBON, like I said, we're using the seascape framework as a means of biogeography. And so what that means, and here I'm showing you at two different time points, the Central California coast, and here is the seascape extent. Each individual color denotes an individual seascape. And you can see, for example, the seascapes expanding in space through time. And what we do with every one of our regional nodes in the NBON is that we work with our regional partners to validate the seascape patterns that we see in space. And then we use the in-situ data and the pattern validation to refine the parameters that may go into some of these regional seascapes. Now, what this allows us to do is some work that is very important to biodiversity, including rarefaction and patch scale. Rarefaction is one of those means that we can, the tools that we use to understand if we are sampling the environment thoroughly enough to assess biodiversity in a region. We also use this as a means of ecosystem comparison and whether or not habitats are changing in terms of their seasonal and interannual extent. We also use this as a means towards real-time cruise planning so that we can track features in the water and go out and sample them if they're deemed unique or important. And finally, we are using these seascapes as an to provide end-user indicators and metrics of habitat changes in people's regions of interest. So again, here is an image of the global seascapes, and here are each of our current U.S. NBON nodes, the regions that they're interested in. And again, this is a static image right here, but you can imagine that each one of these patches is going to be expanding and contracting in time. And each patch, each color here, represents a unique suite of water mass characteristics. And we're also, with our method, we're able to have an attribution of uncertainty. And what this means is, as you look through the color here, we can see that some of the regions are classified with greater uncertainty, so some of the warmer colors here, and then lesser, more uncertainty, so some of the cooler colors here. And so where those regions are overlapping, say we have fronts or water mass mixing, we can see those in space and time by the attribution of uncertainty. I'm going to hand this over to Joaquin now because we've been able to form this partnership with NOAA Coast Watch in order to serve these maps operationally.
Thank you, Maria. As Maria mentioned, one of the partners of this effort is the Coast Watch Ocean Watch program. So I'm the operation manager for the Coast Watch Caribbean and Gulf of Mexico node and Atlantic Ocean Watch. So one of the main objectives of this program is to contribute with data and tools to allow scientists and other stakeholders to better understand the physical, biological, and chemical process in the ocean. So as part of this program, we make available near real-time and historical satellite data sets, but also data from models and field observations are available from our node. So the seascape product is one of these products. So the seascape product provides coverage of the global oceans at 5 kilometer spatial resolution with a time step of 8 days and 1 month. Consequently, we can generate reports and statistics at global, basin, and even regional levels. So essential biodiversity variables are needed to support a large number of biodiversity information efforts, from implementing like monitoring systems, carrying assessments, or develop new biodiversity indicators to be used by decision makers. So the seascape product fits pretty well within the ecosystem structure class, explaining the organization of ecosystems in space, where could be useful to infer, for example, the habitat structure or the ecosystem extent and fragmentation, or if we want to study the ecosystem composition by functional type. So this effort provides a tool to study the temporal variability and the trends for the different seascape classes. And here we include the detection of atypical events. As a first step to achieve operational status, the weekly and monthly fields are made available for general distribution through the different data servers at Coast Watch and Ocean Watch. The average latency is around 1–2 months. The Seascape product is available through Threads and AirDAP, this middleware that allow us to distribute and visualize different products from satellites and models and even observations. And using this, the Threads and AirDAP users can download the products. These are interoperable solutions, so the products can be integrated transparently into the water environments of the users. These water environments can be MATLAB, ArcGIS, RStudio, and also can be visualized using tools like Ocean Viewer, the one that you see there in the slide. This is an interface that was developed in-house at NOAA in Miami, and that provides online tools for integrating the information from multiple sources, including in situ data. You can generate animations, overlay vector layers, etc. And now we are ready to move to a more operational environment, improving temporal resolution as daily, weekly, and monthly fields can be generated using remote sensor data, and also by improving the spatial resolution, especially for coastal and regional studies and applications. Also, and considering that some of the inputs are from sensors that are at the end of their operational life, and thinking about MODIS here, we are working on guaranteeing the consistency and future of the time series by generating similar fields using data from other sensors like VIRS and ORCI as inputs to the system. Maria, your turn.
All right, just to close and just to summarize, so we're using these dynamic seascapes as a metric of pelagic habitat geography, so thinking about things like extent, the location of habitat, as well as how representative that habitat is. We're using these as metrics of biodiversity, habitat diversity, and novelty. So one thing we are realizing through our recent efforts are that the habitat baselines are changing in many areas of the world. So we are working with our partners to see truth and establish rigorous habitat species relationships across the globe. And one of the things we want to ask for people who are in the audience and who are interested in these case studies, interested in this product, to contact us, because we need more validation and case studies throughout the world, and we welcome people's input and partnerships, new partnerships forming in your regions of interest. And that's it. Thank you.
Thanks, Maria. Thanks, Joaquin. Thanks, everybody. Okay, we have time for questions. If anybody has any questions online, go ahead and type them into the chat. You have a question? Laura has a question.
Yeah, I'll start. A question for you, Josh. So you use this method to look at harbor seals, but is it also possible from the photographs you've taken to detect other things like habitat and how that's changing with different surveys, or any other organisms that you can look at abundance from the data you've already collected?
Yeah, thanks, Laura. That's a great question. One of the there are stellar sea lions and northern fur seals present on the Pribilos, but those are being explored and counted through other efforts within the Alaska Fisheries Science Center and different UAS platforms. The EB SenseFly, the fixed-wing aircraft that we flew in partnership with Duke University, we were able to collect some of that really detailed orthomosaic digital elevation model using the structure from motion technique, which provided detailed habitat information that the Aleut community is already using in some cases to inform some of their information about Otter Island, and there's a possibility they could take some of that experience and even use their DJI platform to do some of that same stuff in other parts of St. Paul or maybe even on St. George. So the potential is there, but for now most of our effort has focused on harbor seals. I guess I'd also add we'd like to maybe potentially do some additional stuff in the future, actually using structure for motion or similar technologies to actually get photogrammetry, so length and maybe even some mass estimates for each individual harbor seal, which would be a really great information for us to learn about how healthy these seals might be.
Okay. Thank you, Josh. And then we have a question from Catherine Miller. Question for Brian. What type of cameras, equipment were used for your data collection on the UAS?
Sure. Thanks, Catherine. So the 4 UAS that I showed in my slide, all of that was out-of-the-box technology. There was nothing customized to those packages. The only exception was the 3DR Solo, which had a GPS unit that was built that was RTK enabled. But the cameras and everything else was out of the box.
And Brian, you're doing habitat. Laura asked about habitat. You guys have been mapping habitat, haven't you?
Yes, it's there's great potential there to come up with some very detailed habitat maps, potentially at the genus or species level in some cases. There's potential to look at before and after, restoration events or other natural disasters to assess the changes over time. So those are things we're interested in, and there are certainly a lot of potential applications. I will say one limitation is longevity. So for the quadcopters, the UAS that you see here, the average flight time is somewhere between 10 to 15 minutes, so not a whole lot of time. There are also FAA restrictions in terms of line of sight. You can't, at least for the small UAS, fly beyond that without special permission. So while these are a great tool, there's still a lot of issues to work through to figure out how best to use them, where to use them, and how effectively to use them.
Okay, thanks. Maria, I have a question for you and Joaquin. Can you tell us a little bit about the case studies where people have used your data so far? And for example, it seems like your stuff must be on NOAA's Science for a Sphere. You have such great global data sets.
It would be great. Yeah, we actually, I'm not sure we have it on a Science for a Sphere, Science for a Sphere yet, but we have case studies in all of our regional NBON nodes, and some case studies occurring in South America, Central America, and off the UK right now. Most of our case studies are looking at lower trophic level organisms, things like whether or not phytoplankton or bacterioplankton communities are different across different seascapes. We our partners in the Arctic are using seascapes to determine whether or not zooplankton and seabird foraging patterns may be predicted by seascape boundaries. And our partners in California are using seascapes as a means to determine variability in forage species, things like juvenile rockfish, anchovy, etc. And so, yeah, there's a lot of case studies right now, but we're continually realizing that one, that the habitat baselines are changing, and two, that our understanding of regional variability is really important. So that is to say that our global satellite efforts are fantastic at the global scale, but sometimes the algorithms may fall apart at a regional scale because of several different reasons. But also, sometimes we are not considering all of the local physics when we look at in the very near shore. So there's a lot of room for us to improve and hopefully help regional managers and regional scientists discern differences about their habitats. So like I said, it's an iterative process, and it requires partnership.
Yeah, that's a huge project, global data sets. And I'm going to find the contact for the Science on a Sphere folks, so maybe they can contact you about putting those up.
That'd be great.
Okay. And then Catherine Miller has a follow-up question for you, Brian. Quick follow-up. So the digital elevation models were developed using the altimeter on the DJI. Was this problematic with waves as well?
So no, they were not developed using the altimeter. So that's where the GPS, the PPK, RTK capabilities come in play. What we did was use the ellipsoid height to determine the the depth or elevation to the ellipsoid, and then you translate that using VDatum to a tidal datum, which is what most depths are on the charts. So there's some math involved there. As I mentioned, definitely weather conditions affected the quality of the outcomes or the products. So the clearer, the calmer the water, the better the product. So waves certainly impacted the outcomes and the quality of those DEMs and photomosaics. If you have a lot of white water, you're not going to see what's underneath it, so you can't map the depth.
Does that answer your question, Catherine? All right. Okay. Are there any more questions? Okay. Well, Laura's going to wrap up here for us.
So thank you to all of our speakers for very interesting talks today. And 2 weeks from now, on March 18th, will be our fourth and final seminar in the NOAA Science Report series. We'll feature another sample of research accomplishments, including the social sciences. The lightning talks in this seminar will include talks on improving forecaster and partner interpretation of uncertainty and confidence in risk information, dust storm response, engaging communities with online action planning tools, and using big data to understand data for fisheries. We hope you can all join us there.
Yes, and thanks for joining us, folks online and captioners. Thanks for a terrific job of captioning. Once again, if you're interested in getting a PDF copy of this presentation or an MP4, go ahead and contact one of us listed here. And thanks again, presenters. Hope to see you in a couple of weeks. Bye-bye. Thank you.
Hey, thanks.